Richard James will finish these factorization tutorials with, of course, the last one that we have, and that is Factorization Tutorial 5. Returning to the fundamentals of mathematics as we learn them in primary school, we cannot reduce a fraction unless there is a factor that is common to both numerator and the denominator. No matter what numerator and denominator look like, we cannot cancel unless we can identify factors that are common to both. Factors may not be so obvious unless we factorize. The numerator is in the form of a difference of two squares, and in this particular problem we are required to simplify the expression that we have right here, which is x squared minus 1 over x minus 1. This one. We are required to reduce the fraction. As a matter of fact, the statement of the problem is that we should simplify this expression. Simplifying this expression may mean that we need to expand brackets and combine the like terms. But on this occasion, we have an algebraic fraction. And usually when we have an algebraic fraction, it is usually a requirement that we reduce the fraction if we are simplifying the expression. On this occasion, that is what we need to do. We cannot just jump and reduce this fraction. Well, I can see the end of this problem already. But we should not take an approach in a situation in which we are required to reduce a fraction, and then especially an algebraic fraction, and then just go straight ahead and approach it in any way that we feel. We have to go back to our foundation in primary school. You cannot reduce a fraction unless we can identify a factor that is present in both numerator and the denominator. And that is what we need to do first. Identify factors that are common to numerator and denominator. If we say x into x squared, of course, x is not a factor of the numerator, so we cannot do that. Our approach, therefore, is, if it is possible, write the expression in the numerator and also, if possible, in the denominator in its factorized form. Then we will see factors, and we will see factors that are common to numerator and the denominator. Now, as it is said, the numerator is in the form of a difference of two squares. So we will factorize the difference of two squares. We need to have a factor or factors that are present in both numerator and the denominator before we can reduce the fraction. Therefore, if we can factorize, that may be our best option, because as it is said, factors may not be so obvious unless we factorize. So we have a difference of two squares, and I'm sure that we have factorized at least 20 of them so far. Use the square root of the squares. We will factorize the difference of two squares by taking the square root of the squares. And we have x squared is one and 1 is the other. So take the square root of x squared, we get x, and take the square root of 1, we get 1. And as usual, we will cause those square roots to be separated by, in one case, a positive sign, and in the other case, a negative sign, in any order. And now we have seen the common factors, that is, the factor that is present in both numerator and the denominator, and then we may reduce the fraction by that common factor. The factor x minus 1 is in both numerator and the denominator. We may reduce the fraction by that common factor. And all that is left is x plus 1, which some mathematics campers may not see immediately because of the negative sign separating both of them. the mathematics campus may not imagine that the answer could be x plus 1, but that's what it is. We factorize the numerator that is in the form of a difference of 2 squares, and we eliminate these common factors, and the result is x plus 1. And we will demonstrate how some candidates may attempt to solve this problem. The statement of the problem requires that we simplify the expression that we have right there. We have simplified expressions in previous tutorials. Simplifying an expression usually requires that we reduce an algebraic fraction when one is given, as in this case, or required that we expand brackets and combine like terms. So, in simplifying an expression, we may be required to reduce a fraction, or we may be required to expand brackets and combine like terms. On this occasion, we have an algebraic fraction. Quite likely, what is required is that we should reduce the algebraic fraction that is given. Candidates are usually very happy to see a problem like this in order that they may cancel the x's and cancel the negative 1, like so. So as soon as the candidates see this x squared minus 1 over x minus 1, they say yes, x is common, cancel x. X into x squared is x. X squared divided by x is x. And they say, okay, the negative 1s, they are gone. And all that is left is x. So the occurrences of negative 1 are eliminated all entirely, and we are left with x alone. Such an approach is incorrect because there is no common factor of x in neither numerator nor denominator. So we will not see any common factor of x, because we cannot take a common factor of x in the denominator because x is not common in the denominator. And neither can we take a common factor of x in the numerator because x is not common to the numerator. What we mean when we say it is not common, x is not present in both terms. And here also x is not present in both terms. So we cannot cancel or we cannot reduce by a factor of x because it is not common to both numerator and denominator. The same is true for negative 1. The existence of x's and occurrences of negative 1 in both numerator and denominator does not make them common factors. So although they are present, that does not make them common factor. And we cannot imagine that as long as something is present, it is a common factor, because that is far from the truth. In attempting to reduce the fraction by those terms that are not factors that are common to both denominator and numerator, we made an error. So, in attempting to reduce the fraction by those terms that are not common to both numerator and denominator, we made an error. In order to reduce a fraction by a particular factor, it has to be a common factor of both numerator and denominator. We may want to be a bit technical and say that negative 1 is a factor of everything, which is true. That is true, but applying it in that way in this problem would have caused the end to be worse than the beginning. So we cannot divide through by a negative 1 in that fashion. Of course we can divide through by a negative 1, but not in that fashion. And if we do that, we will have to change the sign of every single term. And that in itself will cause the problem to be worse than the one that we really have there. So what do? We ensure that whenever we are attempting to reduce a fraction, whatever the factor is, be it just numeric or algebraic, we have to have the factor common to both numerator and denominator. Here is another algebraic fraction for which the statement of the problem requires us to simplify. Again, simplifying means that we will reduce the fraction, but we cannot do that without identifying a factor that is common to both numerator and the denominator. Let us therefore factorize the numerator using 2ab as our highest common factor. So we will factorize the numerator by a highest common factor of 2ab. And of course, if we are doing that, we need to divide by ab. And of course, if we are doing that, we need to divide by the highest common factor of 2ab. So we have 4ab squared divided by 2ab, because we are factorizing the numerator by a common factor of 2ab. Each term in the numerator has to be divided by 2ab. So 4ab squared divided by 2ab is equal to 2b, and 2a squared b divided by 2ab, which is the highest common factor of the numerator, will give us only a. So we have 2b minus a, and that is our other factor. And of course, we can see the common ab there. Why can we do that? Because 2ab is a factor of the entire numerator. That is why we may go straight ahead and reduce by ab. Recognizing that ab is a part of one of the factors of the numerator and is the denominator, we may reduce the fraction by a common factor of ab. So go straight ahead and reduce the fraction by a common factor of ab, and we will have 2 left and 2b minus a in the brackets, like we have right there. Before the end of the tutorials, we will take a look at how we may adjust algebraic fractions when we are reducing them, and sometimes we do not have to adjust them. We may go straight ahead and reduce them, and we'll take a look at how we may do that. Let us return to our regular factorization. We will factorize by grouping by first taking a common factor of 3. So 3 is the common factor of the first two that we have right there. So let's go straight ahead. So we have 3g minus 3t. Take a common factor of 3. There's no doubt that g minus t will remain after we take these 3 out. So divide each term by the highest common factor of 3, and what do we notice? That the 3's will go. But before we do that, we need to take a common factor of the other two terms. And we have 2 is common, 2 is common, m is common, m is common. There's no doubt that the highest common factor of the second pair is 2m. And then we will divide each term by 2m. And what do we do? The 3's will go there. 3g divided by 3 is equal to g, and negative 3t divided by 3 is negative t. Take those out, and we have a negative t left. What do we do? Take out the 2m's there. 2m into 2mg, the 2m's will cancel, and we have g, as we say right here. We also have 2mt divided by 2m. The 2m's will go and the t will remain. Do not forget the negative sign there. Those 2m's are gone and the g remains, and the 2m's are gone, the t remains, accompanied by that negative sign, negative t. Finally, the common factor is g minus t. That is our common factor. And what do? We always hold on to our common factor and divide each term by the common factor. And when we divide by the common factor, what do we know? Those are gone. We have 3. And then we have 2m. And that's all there is to it. Now we have another trinomial, and being at the end of these tutorials, we will not bother to go through taking a look at every single pair that will give the product, but we will zero in on the pair very quickly. By now, we should not have to go through the entire system in order to find the 2 component middle coefficients, as we have always done. AC, A is 3, C is negative 8. When we multiply 3 by negative 8, we get a negative 24. The numbers will therefore have different signs because the product is negative. The numbers will have different signs. The sum of the 2 numbers is a positive 2. We may find the 2 numbers as soon as we are able to find the 2 numbers that multiply to give 24, actually a negative 24, and have a difference of positive 2. Do not forget that the product is negative, which causes the numbers to have different signs. The sum is positive. The sum is a positive 2, as we have right there, and the larger number is therefore positive. The 2 numbers are positive 6 and negative 4 in any order that you please. So if you want to say plus 6 minus 4 is equal to a positive 2, or you want to say a negative 4 plus 6 is equal to a positive 2, you may go straight ahead. However, it is important to note that we do not have to go through all of this long and lengthy process anymore, because as a matter of fact, we can do it in our mind. For 24, we can run the factors in our minds, and we will see that 12, 2, a difference of 10, 8, 3, a difference of 5, and then we have 24 with 1, that's a difference of 23, and we know 6 and 4, we have a difference of 2, so that's the 1, and a positive 2 means that the larger one is positive. The expression has its middle term resolved into its 2 components. Begin factorizing by taking a common factor of 3x. So we have them 4 terms right here, common factor of 3x of the first. So the first 2 terms have a common factor of 3x, and we say 3x into 3x squared. The 3 will cancel with the 3. X into x squared is x. 3 into 6 is 2. X will cancel with x, 2. So we have x plus 2. 3x squared divided by 3x is x. 6x divided by 3x is equal to 2. X plus 2. And the second pair has a common factor of negative 4. Obviously, negative 4. And we say negative 4 into negative 4x. Negative within negative is positive, and the 4's will cancel. We have x. Negative into negative is positive, and 4 into 8 is 2, so x plus 2 again. We have it right there. Negative into negative is positive, and of course the 4's will cancel, and we have the x. Over here, negative into negative is positive, and 4 into 8 is 2. Now we have a common factor of x plus 2. X plus 2. So we say x plus 2 is our common factor, and we say x plus 2 will cancel with x plus 2 because after identifying our highest common factor, we divide each term by our highest common factor. So we say x plus 2 into x plus 2 is 3x, and we say that x plus 2 will cancel with x plus 2 and will give 3x, and x plus 2 will cancel with x plus 2, and we will have a negative 4 because each term is divided by the highest common factor. After we divide each term by x plus 2, the other factor will be 3x minus 4, and we have them highlighted right here. So the other term, the other factor will be 3x minus 4. The factorization problem that we have right here is analogous to one that we saw in tutorial 3. We may therefore solve by analogy, taking the common factor of 3 that will cause the resulting expression to be a difference of 2 squares, then proceed to factorize the difference of 2 squares. So we have solved a problem like this before, so we do not need to keep going around in a circle. We take a common factor first and see what happens next. So take our common factor of 3, and we know that 3 into 3x squared, just x squared, and 3 into 27 is 9, x squared minus 9. 3x squared divided by 3 is x squared. 27 divided by 3 is equal to 9. There we have x squared minus 9, and we will factorize that by taking the square root of the squares, because we are factorizing a difference of 2 squares. So factorize the difference of 2 squares by taking the square root of the 2 squares. The square root of x squared is x square, and the square root are inverse operations, will eliminate each other, and we have square root of 9 is equal to 3. So as usual, we will place them in their pairs of brackets, and we will separate them by a positive sign in one case and a negative sign in the other case. And that's all there is to it. The statement of the problem says, factorize completely. We factorized by taking a common factor, and the resulting expression is a difference of 2 squares, which we proceed to factorize also. And that is what we need to do when we can factorize. Again, please do not let us have to analyze a problem that is such a close analogy to one that we have solved before. If there is a very new circumstance coming out of the problem, then let us analyze it. However, we may adjust a previous solution to fit this one because of the close relationship between the two problems. In other words, let us not reinvent the wheel. Life is like this, in which we have to solve problems that we have solved one that is similar to it. Therefore, we will make use of the similarity that exists between two problems in solving the second one. So we will solve by analogy, and that is what we should do as long as we can. Always solve by analogy if we can. So we will just make use of the highest common factor, and of course there's a great resemblance between the way that we have the terms that are in the expression. So AB is our common factor, and we will know that because of the A squared here we will have A coming, and because of the B squared we will have B. So we will have 5A in the first term and B in the next one, and that is by experience, or we may take a good look at it and see that it is quite obvious. So 5A squared B divided by AB is equal to 5A, and AB squared divided by AB is equal to B. In order to be not just explicit, but if the expression was a little bit too cumbersome, let us put that one under the microscope. So we have the common factor of AB, and we will divide each term by the highest common factor of AB. And let us see what we make of it. So our highest common factor always goes back. It's always in the expression. Our highest common factor. What do we do now? We divide each term by the highest common factor. And there's nothing to cancel the 5, so the 5 will go right back. And then we do what? A squared divided by A is A. A squared divided by A is A. Goes there. And the B's cancel each other. So we do not need to make further mention of the B. As it is always said, no say nothing. So for the B's, we no say nothing. And we move to the next term. The A's cancel completely. We no say nothing. And B into B squared is B. And do not forget, the sign of separation is positive. So a positive B right there. Your favorite. We may now bid good riddance to the difference of two squares, because although we are at the penultimate problem in these tutorials, we are seeing the last difference of two squares. At least we know how to factorize it. Before we finish these video tutorials, we will show that the difference of two squares is actually a quadratic expression, if we have not done so already, and factorize it as such. So, as a matter of fact, we have shown in a previous tutorial already that a difference of two squares is actually quadratic. We converted it into its trinomial form, and then we converted it into its quadratic form, and we factorized it by taking two at a time. Factorization by grouping. But here, we will not go through all of that because it is not necessary in an examination. We will go straight ahead and take the square root of the squares. So proceed by finding the square root of the squares. They will be enclosed in brackets and be separated by a negative sign in one case and a positive sign in the other. So we have square root of 9k squared. Square root of 9 is 3. Square root of k squared is k. And no doubt, the square root of 1 is equal to 1. So we put the 3k and the 1, the 3k and the 1, and we will separate them by a negative sign in one case and a positive sign in the other. And that's our final difference of two squares for all of these tutorials. Now we have our final trinomial and our final problem. Again, we will not go through all of the detail in resolving the middle term into its two components. The product AC is 2 times 2, and that is equal to 4, and it is positive. The result is positive. This tells us that the two numbers will have the same sign. Also, the middle term is negative. This tells us that the two terms that have the same sign are actually negative, because the two numbers will have the same sign because the product is positive, but the sum is negative. There is no way that you can add two positive numbers and get a negative 5. The two numbers have to have the same sign. The two of them have to be negative. Too often, students come to the conclusion that the two terms have to have the same sign, and then on seeing a negative sign here, they say one is positive and the other is negative. So they use a positive and a negative after arriving at the conclusion that because of the positive product, the two numbers must have the same sign. We are maintaining that the two numbers have the same sign, but because the sum is negative, as we have right there, then the two numbers are negative. So the result is positive. The two numbers are of the same sign. Also, the middle term is negative. This tells us that they are both negative. As long as the two terms have the same sign, we have an addition problem. Also, the sum is larger than the product. This tells us that one of the numbers is 1. Yeah, one of the numbers is 1 because the product is 4 and the sum is 5. When the sum is larger than the product, one of the numbers is 1. So that eliminates quite a few options. As a matter of fact, we did not have many to begin with. So that eliminates the other option. So one of the numbers is 1 and the other one actually has to be 4. The negative versions. Since one of the numbers is 1, actually negative 1, then the other number must be 4, which is actually negative 4. The two numbers are therefore negative 1 and negative 4. And these will be the two coefficients of the component middle term. So the expression has its middle term resolved into its two components, which is a negative 4y and a negative 1y, which is a negative y. So those are the two middle components. And we will factorize immediately by taking a common factor of 2y. So the first two terms have a common factor of 2y, and we know that our common factor 2y there, 2y into 2y squared, the 2's will cancel, y into y squared is y, and 2y into negative 4y, we have a negative sign there, 2 into 4 is 2, and the y's will cancel. So we will have y minus 2. 2y squared divided by 2y is y, and negative 4y divided by 2y is equal to negative 2. The second pair has a common factor of negative 1. Now, we could say a common factor of 1, but we have established a rule of taking the sign that begins the second pair. So if we have two, well, we generally have two terms here. The first one in the pair is negative. We take our common factor as negative. So we have a negative 1 there. Negative into negative is positive, and negative into positive is negative. So we will have a y and we will have a 2. The first one is negative into negative is positive, and the second one is negative into positive will be negative. So negative y divided by negative 1, negative divided by negative is positive, positive y. 2 divided by negative 1 is equal to negative 2. So we have now our common factor of y minus 2. So take our common factor of y minus 2. We can see, surely, y minus 2 is a common factor there. And as usual, we may just go straight ahead and put 2y minus 1 as the other factor, as we have done before. But we are highlighting those terms. After we divide each term by y minus 2, the other factor will be 2y minus 1 that we have right there, because we are cancelling the y minus 2 with the y minus 2. We'll get 2y. Cancel the y minus 2 with the y minus 2. We'll get a negative 1. And we are at the end of the problems associated with the tutorials. But we are not at the end of the tutorials. We are about to take a look at something that I think needs mentioning. So we will not hesitate. We will go straight ahead. We have discussed the fact that we cannot reduce an algebraic fraction unless there is a factor that is common to both numerator and a denominator, in the same way that we treat an ordinary fraction. So we cannot reduce this fraction unless we have a factor that is common to both numerator and denominator. Let us factorize the numerator by taking a common factor of 2. And we will not go into the details of factorizing by a common factor of 2 after we have finished so many problems in factorization in the entire 5 tutorials. So we have 2 times all of x plus 2. That's the result of factorizing the numerator, and we are dividing by 2 the denominator. So what do? We are reducing the fraction now because we are sure, and it is very clear, that we have a common factor of 2. So let us reduce the fraction by a common factor of 2. They are gone. So the common factor of 2 is gone, and all we have left is x plus 2. As a matter of fact, if we wanted to be technical, we could place 1 here and put 1 there and say 1 times all of x plus 2, and we will just get x plus 2 because 1 multiplied by anything is that same thing. Also, if the denominator were 1, x plus 2 divided by 1, anything divided by 1 would have been the same thing. So we can just say that the result is x plus 2 when we factorize the numerator and reduce by a common factor that we see that exists. The result is x plus 2. Now, what do we have here? We really have no need to factorize if we can see the common factor of 2 in the numerator and the factor of 2 that is present in the denominator. So if we can see a common factor of 2 here and a factor of 2 down here just by inspection, then we should not really need to go through the process of having to factorize. So if that is so, then we may reduce by the common factor of 2 in this manner. So we may divide each term in the numerator by the factor that exists in the denominator. If that is what we see, that we have a common factor of 2 here, then we may just go straight ahead and say 2x divided by 2 and 4 divided by 2. So 2x divided by 2 is x, and 4 divided by 2 is 2. So 2 into 2x is x, and 2 into 4 is 2, and that's all there is to it, as long as we can see that there's a common factor. If the 2 is not common in the numerator, we could not do that. Why may we legitimately do that? That is what I'm saying now. We have a question. Why may we legitimately look at this expression and say 2 into 2x is x and 2 into 4 is 2? Why may we do that legitimately? Because apart from the fact that we need to take a common factor, and we can do that by factorization, and I am saying also that we could have just said 2 into 2x, x, 2 into 4, 2. Why can we do that? That is, why may we use the entire denominator or a term in the denominator to cancel each term of the numerator rather than factorizing the numerator? Why can we do that? Because if we can do it, it has to be legitimate, as long as we are attempting to solve the problem correctly. Whatever we are doing has to be legitimate. So why is it legitimate? It is legitimate because of this reason. It can be done because dividing an entire expression by 2 is the same as taking half of the entire expression. So we are dividing this entire expression by 2. We are dividing the entire expression by 2. It is the same as taking half of the entire expression. I am sure that no one will have any difficulty with that. And if we are taking half of the entire expression, rest of the expression being enclosed in brackets, we may apply the distributive law, saying that we are saying half of 2x and then half of 4, which is just expanding the brackets. So by the distributive law, a half is distributed to each of the terms that is inside of the brackets. So a half of 2x is x and a half of 4 is 2. That is why we can do it from here and say 2 into 2x is x and 2 into 4 is 2. We can do it from right here rather than going through the factorization process. As long as there is a common factor of the numerator that is equal to a factor that exists in the denominator, we may reduce the expression without factorization. So we may do that without factorization. Although we may do it without factorization, when I am using my examples, I usually throw in the factorization process first. Even if the expression is a bit more complex, we may apply the same principle. We will, however, make use of factorization first. So we may do the same thing, but let us factorize first, taking a common factor. Is there a common factor of the numerator? Sure there is. A common factor of 5. So let us factorize the numerator by taking a common factor of 5. And we will not go through the entire process because we have done that on hundreds of occasions already in these tutorials. So we have, let us do it anyway. Common factor of 5. 5 into 20 is 4 and the x returns. 5 into 15 is 3. That's all there is to it. So if we have the factor there, let us reduce the fraction by a common factor of 5 because we have a factor of 5 now. We may go because we have 10 also has a factor of 5, so we may go straight ahead. Of course, the 5 will cancel completely, and 5 into 10 is 2, and we have discussed in these tutorials already what we mean when we say something cancels completely. So we have 5 into 10 is 2, and the 5s are gone, so we have 4x plus 3 over 2. And there is the entire expression, the original one. As we said before, we do not need to factorize if we see a common factor in the numerator, and that is equal to the denominator or a factor that exists in the denominator. So look at this. The numerator has a common factor of 5 and the denominator has a factor of 5 also. So we may say 20x divided by 5 is 4x, 15 divided by 5 is 3, 10 divided by 5 is 2, and then we have what? 4x plus 3 over 2 again. So we did not really have to go through the factorization process. We may look at it and see the common factor and divide right through both numerator and denominator by the factor of 5. And we know that if we affect the numerator and denominator of a fraction in the same way by multiplication or by division, that does not change the value of the fraction, but it changes the appearance of the fraction, causing it to be simpler. If numerator and denominator are algebraic, the treatment is the same. So if the numerator is algebraic and the denominator is algebraic, maybe before we arrive here, some mathematics campers would have been asking the same question. Suppose both numerator and denominator were of the same level of sophistry. What would we do? And we could do the same thing by factorization, taking a common factor of 3 because the numerator has a common factor of 3 and the denominator has a common factor of 3. And after doing that, it is easy. We just reduce the fraction by the common factor of 3. The 3's are gone, and all that is left is x plus 2 over 3x minus 4, and we write it right there. And we always say that as long as we can identify a factor that is common to both numerator and the denominator, there is really no need for us to go through the lengthy process. So 3x plus 6 over 9x minus 12, what do? We identify, well, we did that when we were factorizing already. Identified a factor that is common to both numerator and denominator. So we could have said 3 into 3x is x, 3 into 6 is 2, 3 into 9x is 3, 3 into negative 12 is negative 4. We could have done that without going through the factorization process. So, after identifying a common factor of the numerator that is also a common factor of the denominator, we may proceed to divide each term in both numerator and denominator by the common factor. So we have 3x divided by 3 is equal to x, and 6 divided by 3 is equal to 2, 9 divided by 3 is equal to 3, and negative 12 divided by 3 is negative 4. Right. And we have that x plus 2, 3x minus 4. Generally, it is safer to factorize. We will actually see the common factor. The other method may be quicker, but subject to error. We have to be doubly sure that the common factor exists and take care to divide each term by the highest common factor. So we have to ensure that the common factor exists. And well, I think that factorization is safer. We try to factorize the numerator by a factor, and then that factor we identify to be in the denominator also. We can go straight ahead and do that. If we factorize one and then cannot factorize the other, then we know that we are at a crossroad. Well, not a crossroad, but a dead end. So all we need to do is ensure that the factors exist, and then we may just simplify in one step. Or we may take the safer route, which is we factorize by taking the highest common factor of the numerator and the highest common factor of the denominator and make use of those factors.